And we're back. Welcome back and happy Thursday. Today, we will go over some guidance, in particular MATLAB guidance, for implementation of PLA, Perceptron Learning Algorithm. But before we begin, some administrative bits. Project number 3 is on the blackboard. It will be due on Thursday, the 18th of this month, at the usual 11:59 and 59 seconds, 1 second before the stroke of midnight. Okay, we talked about the credit approval problem, and in this we had a customer record in D dimensions, and each one of the features of a particular customer record or vector consisted of one of D many attributes that was obtained from the credit application of a single customer for that particular financial institution. Corresponding to this D-dimensional input vector, we had a D-dimensional linear model, our perceptron, and that linear model is described by D-dimensional weight vector consisting of W1, W2, up to and including WD. Now these weights uniquely define a particular linear function, our linear hypothesis. We also talked about a threshold T, and that threshold T is the minimum score or weighted sum between the weight vectors and the features for which someone is approved for credit. And so we take that weighted sum, x1 times w1 plus x2 times w2 up to and including xd times wd. We sum all together all those terms. We get a value, a real value. We compare that against the threshold to determine approval. If you're less than that threshold, that score, that weighted sum, it's denial. We call approval a +1 label, our positive examples. We call denial our -1 labels, our denial, our negative examples. And so we took a closed form expression for a hypothesis, which was the score minus the threshold. And if that quantity is greater than 0, sign is going to return a +1, otherwise sign returns a -1. And so we clean this up a bit by absorbing this threshold minus t with a constant w0. And we also included a dummy variable x0 whose value is fixed to 1. We ended up with the following expression, our score, plus the term w0 x0, made the observation that it's the same terms that are in this score. So we folded that into the summation, changing the index, and we get the sign of I goes from 0 to d, wi times xi. In vector form, we observed that this new augmented weighted sum, starting at index 0, is the same as the inner product, W transpose X, where W is our augmented weight vector, augmented with W0, and X is our augmented feature vector, augmented with X0. All right, so then we talked about our PLA update rule. And this PLA update rule, W gets W plus YI XI, corrects for a misclassified point XI. And so here we think of that as moving the decision boundary to correct for an incorrectly classified point on the wrong side of the decision boundary. And so when we do this, this results in a sequence of different weight vectors or sequence of different hypotheses that we're testing to see which one most closely corresponds to the labeling of the ground truth, unknown ground truth target function. And so let's take a look at how we might implement this in MATLAB. So we start out and we have our data file, and our data file on disk is going to be represented in the following fashion. Let's assume we have each one of our vectors, xi. It's in 2 dimensions, so they're going to be drawn from 2-dimensional real-valued feature space. So what that means is that each x value is going to consist of a first feature, xi1, and a second feature, xi2. So that's the first feature and the second feature of the ICE input. And so how we arrange this on disk is in a CSV file. And the CSV file consists of the following. Each row is going to contain one of our vectors x. And so in the first row, we have our x1 vector. And we're going to adopt the convention that these are transposed, because we're going to make the assumption that each one of our vectors, xi, is going to be, by default, a column vector. So that's going to be xi1 and xi2. So given that's the case, if we compute the transpose, xi transpose, that's a vector, is going to be the row vector version, xi1 and xi2, the row vector version of our input vector. So now if we have our x1 transpose, that row vector, x2 transpose, that row vector, all the way up to and including x, let's call it big N many vectors in our data set. Now, that's the first two columns, because each row is a vector, and recall, each one of these vectors has two positions. It has the first feature, the projection on the first axis, and the second feature, projection on the second axis in feature space. And so it's the convention in CSV, when you store your data set where the data points are in R2, two-dimensional real value space, you list them as they're transposed in the CSV file so that each row of the CSV is occupied by one of these vectors. So now that represents the first two columns of that CSV file. The third column is going to be the class label. And so for a particular vector xi, we're going to have an associated class label yi, where each one of those class labels, yi, is either a +1 or a -1. +1 means positive example. -1 means it's a negative example, the denial, if it's negative, approval if it's positive. So this is our label set. And this label set is going to be a so-called binary decision problem. And it's called a binary decision problem because the label set is of cardinality 2. We only have two labels. All right, so given that's the case, we also have in the CSV file that third column is going to either be a +1 or a -1, i.e. the label for that particular input vector from your historical data. And so for the ice vector, xi transpose, we're going to have the corresponding yi, which is +1 or -1, corresponding to the ground truth label assigned by the unknown target function, the ground truth label for that ice input vector. And so when we take our CSV and we read it into memory, we're going to get a matrix, and that matrix is going to consist of the data values, x1, x2, transpose, up to and including xn transpose, along with that third column, the yi values, ±1, ±1. Okay, so the first order of business then is to separate out the data portion from the label or the target portions. And it's sometimes called the targets because it's the label's output by the unknown ground truth target function. So in that particular case, what we end up with is two pieces consisting of each one of those vectors, x1 transpose, up to and including xn transpose, and another vector consisting of all the target values, y1, up to and including y big N. Okay, so each one of these rows in that split off data submatrix is going to have n many rows for the n many input vectors, and the number of columns is going to be 2 because this is a two-dimensional feature space representation. Each of these vectors has 2 positions, the first feature and the second feature. This target is going to be n rows by 1 column because it's just a single scalar, +1 or -1 in each case. So now we take our data, and remember, when we talk about our hypothesis, h of x is equal to sign, we said W transpose x. Now, in this case, the W transpose is the augmented weight vector. And we're going to assume our convention is going to be column vectors. And we took our weight vector, which consisted of W1 up to and including WD, and we augmented it with W0 to absorb the threshold. Likewise, for our x vector, this is really x augmented. And assuming the default is column vector, we had started out with x1, the first feature, up to and including xd. In this case, d, our dimensionality, is 2. But we augmented that with x0. And so if we compute W transpose x, sign of that W transpose x, we can calculate the output for that hypothesis. Now, of course, for efficiency's sake, we don't want to use just one x vector at a time. We want to do that in one fell swoop across the entire set of inputs. So we're going to take our data and we're going to build something called a design matrix. Design matrix. And a design matrix is nothing more than a matrix whose rows or columns are going to be the individual data points. And so we're going to start out with some big matrix X, and what we're going to do with X is we're going to place in each of its rows or columns, in this case we're going to choose columns, each one of our input vectors. So we're going to not use the transpose version, we're going to take the transpose of data, so we're going to say data transpose, and when we do that, we're going to end up with x1 as a column vector. We're going to end up x2 as a column vector, up to and including xn as a column vector. Now, as column vectors, we want to make them augmented. And how do we make them augmented? Well, we make them augmented by putting a dummy variable x0 here, 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 all across our data set. So if we do this, we take our original x and make an augmented version of our data matrix, our design matrix, and we then have our data transpose, which gives us all of those columns consisting of x1 vector up through and including xn vector. And then we're going to include with that another vector, and that particular vector is going to be a vector of all x0s. And we're going to call that the x0 vector. And this is going to be of rank n, because we have n positions. Now, in that case, what we can rename each one of these columns of design matrix x-aug, we can call this x1 augmented, because now it includes this x0, and we can call this xn augmented, because it also includes this x0. And so we can take our design matrix and make it augmented, and we're going to call this big X aug. That's our augmented design matrix. It's a column matrix. Each of the columns is the augmented input vector across the entire data set of size n. So now that we have this, if we want to compute h of x on the whole data set, let's see how that plays out. So we said h of x now let's compute h of x on big X. That's going to be sine W transpose times big X, and it's going to be that X augmented. So let's see how that plays out. So we have our W. We said W is augmented, so W transpose is going to be a row vector consisting of our W naught up to and including WD. And then we set our X augmented, and let's call this W aug, just for the sake of correctness. X augmented, we said, is going to have X1 vector augmented up to and including Xn vector augmented. So if we do this multiplication, W augmented transpose times X aug, we take this vector W, multiply it by X1 aug, this vector W, multiply it by X2 aug, this W vector times X3 aug, and so forth, up to and including this W vector Xn aug. And so what we end up with is a vector output. Let's call that Hx, and that output is going to consist of values equal to W aug transpose times X1 aug. That's one value. The next position is going to be W aug transpose times X2 aug. That's another value. Up to including that last value, it's going to be W aug transpose, that vector times X big N aug. And that's going to be that last value. And so this is going to be the output of our hypothesis on the first X input vector, the second X input vector, up to and including the nth input vector. And each one of these values is either going to be positive or negative, so that when we take the sign of each of these values, positive or negative, we're going to get back either a +1 or a -1 for each one of these products, +1 or -1. And so how we compute our hypothesis evaluated on the whole data set is by doing W transpose X, where that X is now that augmented, that design matrix. And that allows us through MATLAB very easily to apply this evaluation of H of X on the entire data set in one line of MATLAB. So now that we do this, we're going to get a vector, and we call that vector Hx. And this vector, let's assume it's either +1 or -1, +1 or -1, dot, 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 +1 or -1. And this is H of X is going to have n many entries, where n is the data set size. So if we want to know where the hypothesis disagrees with the target function, we go back to this target value and we compare the target value with H of X. So essentially we want to find all those indices where H of X is not equal to the target vector. Now, of course, the target vector, if that's a column vector, you have to transpose it so that they're both row vectors. And this find is going to output, and there's a MATLAB command to do it, it's going to output an index representing all of the offsets in that n vector where that condition is true. So what's it going to do? Let's say if, here's the target. If the target were, let's say, -1 and it didn't match, and we're +1, it didn't match, it's going to return back offset. Find is going to return back offset 1, offset 2, and let's say everywhere else it agreed, and then that's going to be it. And so what this find does, it allows you to find the index into the original data set corresponding to places where h of x, the working hypothesis, disagreed with the unknown target function's label. Okay, so now that we have this, we know that misclassified index, misclassified indices are going to have some values. Maybe it's index 1, index 5, index 9, index 11, and so forth. So now that we have that, when we randomly select a misclassified index for the PLA update, we're going to get the size, num misclassified, length, or the size of the misclassified indices. And then from that, we're going to select one of those indices in the interval between 1 and that size of the misclassified indices, num misclassified. And then from that random integer, we're going to now go into our data array and select whatever xaug, we're going to say the row is going to be a wildcard because we don't care about the features, and the column is going to be that index A. So we want to pull out that misclassified index. Okay. And then A is going to be misclassified index, whatever that position was. So we're going to use whatever we pick here, that's going to be the one we're going to use as the column in xaug, which is the feature vector. Because remember, xaug is a column matrix. All right. So let's try this out in MATLAB, and we'll see how it looks. All right. So let's meet you in MATLAB. So we're here in MATLAB, and I'm going to go through the PLA skeleton code, showing you some of these things that we just talked about in MATLAB. So we have our CSV file, and we're going to have 100 positive examples and 100 negative examples, so 100 points per category. And we start out, we initialize the random number generator with a defined seed because we want to have the same random number sequence across each run of this PLA implementation. We're going to read in our data. That's going to give us this matrix. So let's go ahead and read in the data. And when we're reading the data, all the data, remember, it's 200 rows because we have 200 total data vectors in 2 dimensions. 100 of them are positive examples, 100 of them are negative examples. And then you see 200 by 3 because we have 2 features for each vector, but a third entry is going to be the target function's ground truth label assigned to this input. So we have 200 by 3. If we were to look at, for example, all data, you'll notice here we have the first feature, the second feature, and then the class label. If we scroll up a little more, first feature, second feature, and the class label. So now we're going to take our data and we're going to extract it out so that we get the data points in line 32 separate from the target values in line 37. So let's go ahead and look at that. Continue. Here we have the points. It's 200 by 2. Each row only has 2 features. And then if we look at targets, that's a column vector with the class label. We have 200 of them, 1 label for each one of those 200 of the input vectors. And so now we're going to take the points and we're going to transpose them because we want to use that as the basis of that X augmented column matrix. that design matrix. And so we take the transpose of points and we take the transpose of targets, because we're going to use that for comparison later on. We go ahead and we plot the data, initialize our weight vector, and then here we build our x naught. And this x naught was dummy variable with all values set to 1. So we have 1 by n. Remember, this was a row vector, and that n is the total number of data points. We had two categories. Each one had 100 points per category for a total of 200. So we take that x naught, we first instantiate or allocate an array of zeros, and then we add 1 to each position. So there's our dummy variable x naught. So then here, this is just some convenience work to have good initialization so that it plots well when visualizing it. So we randomly select some value between a high and a low, and then we set those as the initial weights at time t0 for the algorithm. So then in a series of rounds, number of iterations, we build the augmented matrix. And we do that by, you'll notice here, points. Let me run the debugger. Points is going to be that data matrix. And you notice it's 2 rows by 200 columns. Each column is one of those 200 many two-dimensional vectors. And so this is our column matrix, our augmented column matrix that we're building here. And so at this juncture, we have each one of those two-dimensional feature vectors in a column for this design matrix. And then we're going to augment it. We're going to paste in that row vector of x naughts. There's our row vector for x naughts, the class labels. And now this is going to give us our augmented column matrix consisting of our design matrix, our data points. So this is our set of data points. It's now 3 by 200. If I were to list out xaug, I would see the dummy variable x naught in the first row, and then in the second row, the first feature, in the third row, the second feature. So absolutely, these are column vectors, and I've just set the x naught dummy variable for each one of these two-dimensional column vectors. So now there are three-dimensional column vectors in this column matrix, our design matrix of augmented vectors. So now I set my W vector, and my W vector is my weight vector augmented, and it is a column vector. And now I compute h of x, sine W vec transpose, that single quote is transposed in MATLAB, times xaug, my column matrix. So I go ahead and I continue on its step, and you'll see I compute my h of x. So now I bring up my figure, and I see, let me bring it to the foreground, figure 1. So now that I have my linear hypothesis, let's look at h of x. So I'm going to continue stepping through a little bit. Step, step. Let me bring the figure back to the foreground. So now I computed my h of x. My h of x, you'll see sine W vec transpose times xaug, and I get my outputs of the working hypothesis. Now that I have these outputs, I want to compare them to the targets. Now, the target is a column vector, and it's all of the ground truth targets. So let me say target row vector, target row vector is equal to target, I'm going to transpose it, so target row vector is going to be a row vector. And you notice it's either +1 or -1. That's the ground truth target function. H of x is the output of the working hypothesis. So I want to find misclassified misclassified, or misclass, is equal to find wherever h of x is not equal to, that's not equal to in MATLAB, tilde equal, and I forgot what I called it. It's not equal to xaug. I think I called it misclass. No, that is misclass. I called it targ row, I believe. Let's see. Let's go into the history. Targ row vac. There we go. Targ row vac. Okay, misclassified equals targ row vac. So if I look at misclassified, those are all the indices of the misclassified inputs. Now, that's quite a few. I have just about every index in there, not all of them. I have 174 out of 200. But if we look at figure 1, we notice, yeah, there are quite a few misclassified. So there are many that are misclassified up above here. There are many that are misclassified down there. So yeah, quite a few, 174 out of 200. That's not doing very well. So now what we would do is we have our misclassified values. So now we want to randomly select one of these misclassified. So we have random. So let's do it this way. So let's say random, let's see, we have num misclassified is equal to the length of misclassified. So that's 174. And now we're going to say my selection is equal to randy, random integer, between 1 and num misclassified. So I'm going to randomly select one of those indices. There we go. So my selection says the 111th. So my selection is equal to misclassified, the 111th one. So that's 1, 1, or cell. And just because I know it's a row vector, I'm just going to say 1, cell. So my selection is going to be 120th one. So then what I would do, when I do my PLA update, I'm going to select my cell. So let's try this out. If we do this, we're going to here, when I compute my h of x, I plot my data, okay, and now I'm going to select a misclassified point. So what am I going to do? In this particular case, in the code as it stands, I select a randomly selected point. And you'll notice, if I continue my execution, let me remove the breakpoints, it just jumps around, right? Because I'm not selecting a misclassified point, I'm selecting any point, which is not correct. But if I were to change this, we would see that by selecting a misclassified point, you are now getting your PLA update to function properly. All right. So with that, rather than give away the code, you have enough that you need in order to solve the problem. So let's stop here, break, and meet you back in PowerPoint. So we're here back in PowerPoint, and that's all I had for today. Some useful tips for implementation of PLA learning. All right, so with that, as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.